3 wants us to compare models. Sometimes one model is better than another, and that's going to have to be kind of up to you. You're going to have to really look at R and think about what the data means. Let's use this in problem 3, food production. This graph shows the quadratic model for the milk production of the dairy farms. So this, see this graph right here? This is the graph of the quadratic, okay? We did linear. This is the quadratic model. The reason they use that is because they gave us 3 points, okay? The reason, I'm going to say it one more time, the reason they did the quadratic is because they gave us 3 points and they went back to the degree of 2. Given that both the linear and the quadratic models fit pretty good, which seems more likely to represent? So which one's better? In other words, which equation is better? The linear one from problem 2, or this quadratic equation in this problem? That's the overall question. Which equation do you think represents the data better? The reason that probably the linear would be better, and if you're wondering what the linear looked like, it was probably something like this. It's just a straight line. The linear is a better fit. Now you might wonder, why is the linear a better fit? Because it tends to go up. Okay, it would be a straight line, something like that, following the different points around it. Now, why would the quadratic not be as good? Well, look at the quadratic. Look what happens to the milk production after, what was that year? That was 2005. Look what happens to the milk production after 2005. They're saying that milk really starts to take a decrease. It seems to imply, I'm going to say milk starts to decrease quickly. That doesn't make a lot of sense. Okay? So you really have to think about which one would be a better fit. In this one, the linear would be better because, yeah, milk production is going to continue to rise. The quadratic is not such a great example because the quadratic, yeah, it shows that it goes up, but then it starts decreasing. So the quadratic is really only good until it starts to come back down. Let's look at the got it. For the milk production of the Wisconsin dairy farms since 1900, if 4 data points were given instead of 3, would a cubic function be best? So they're saying, would this graph be better? Well, pretend that the 3 points were inside of here. Or the 4 points in this case they're saying. If the 4 points inside of there, do you think that this is a better picture of milk production? Okay. Is this a better picture of milk production? What do you think? This line starts to increase really, really fast. I don't think that the milk production has necessarily gone up that quickly. I don't think it's gone up like exponentially. So this is not better. Why? Because after the same mark of 2005, it would increase way too fast. Okay, let's move on to problem 4. Cheese consumption. This table shows the annual consumption of cheese per person in the United States for the selected years of 1990 to 2001. Use the cubic regression to model the data with the cubic function. Graph the function with the scatter plot of the data. So if we take a look here, see these points? They have already put this in for us. They already came up with the equation. See this graph? This is the equation on a graph. It fits pretty well, doesn't it? Yeah, absolutely. Let's move on and see what the questions are going to ask of us. Use this model in part B. In fact, we better write down what the equation was, okay? Let's write down this equation. It would be y equals 9.24 times 10 to the negative 5 x cubed. The reason I did times 10 to the negative 5 is that e minus 5 there. Minus 0.00958 x squared plus 0.3106 x, and then d is plus 1.8021. So this is the equation. And look how close r squared is. See how close r squared is to 1? That's a pretty good fit. Let's take this equation and copy it down onto this page. Okay. It was y equals 9.24 times 10 to the negative 5 x cubed, because that was the value of a, minus 0.00958 x squared, because that was the value of b, plus 0.3106 x, because that was the value of c, plus 1.802, because that was the value of d. This is the equation. They want us to plug in 1980, 2000, and 2012. As we continue in this problem, it's really important for you to note something about what the book did here, since I took the book answer. They made x equals 0 represent 1900. Okay? So since they want us to plug in 1980, that means we plug in 80. Okay, because 1980 is 80 years away. All right, same thing for 2000. 2000, we plug in 100. And again, this is because I'm using the book's formula. And then for 2012, we need to plug in x equals, would be 112. All right, so let's put these values into our calculator and come up with the answer. So you do 9.24, and then the x value here is, or excuse me, we need the 10 to the negative 5th power, and then we plug in x, and x is 80, and we're going to need to cube it, minus 0.00958 times, our x is 80, and we need to square it, plus 3.3106, x is 80, plus 1.802. So we can see that in the year 1980, it is predicted that the average American consumed 12.6 pounds of cheese. That's a lot. But let's keep going. Let's plug in 100 now. So anytime I see an 80 on my calculator, I'm going to cheat and plug in 100. So I'm doing the same thing, I'm just making it 100. Okay, that should be good. All right, so in 2000, it is predicted that it was 29.5 pounds that were eaten by each American. Now, if we look at this chart, so far, it's matching pretty well. If we look at the year 1980, it would be between 10 and 25. That matches pretty well. Between the year after around 2000, as I get 29.5, that matches pretty well. So far, our data is really accurate. Now let's plug in 2012. So in our calculator, instead of plugging in 100, plug in 112. And I get 46.2. Let's think about what that means. And what I'm going to do is I'm going to pull this chart out, and we're going to talk about if that makes sense. Well, I like the 12.6 and I like the 29.5 because they really do fit our data. But I'm looking at this 2012, and that is increasing so much in a little bit of time. In fact, I bet if I were to plug in like 2020 on my calculator, I would get some ridiculous value. So we should really note here that this is really extreme. And anything after that is also going to be extremely high. For example, let's plug in the year of 2020. So I would be plugging in 2020. Yeah, I don't think that after maybe 2000 this is going to be too accurate because it is getting extremely high, extremely fast. So our data probably isn't going to be very good past 2000. And what is the reasoning for that? It gets extremely high, extremely fast. And now you might be wondering why. Why did that happen? It's because we have a cubic functions. Cubic functions do that. Okay? Cubic functions get extremely high, extremely fast. So really, cubic functions are only good for so long once we use it for estimating.